Hello and welcome. In this video, we'll be exploring some fundamental concepts and functions that are crucial for your IBAA-HL studies. By the end of this session, you will be able to: first, determine if a function is even, odd, or neither, and understand the graphical implications of each. Second, construct and interpret sign diagrams to analyze the behavior of functions. And third, solve inequalities using both algebraic and graphical methods. Let's get started with our first topic, even and odd functions. First, let's define what makes a function even. A function f of x is called an even function if, for every x in its domain, f of negative x equals f of x. In other words, plugging in a negative value gives the same result as plugging in the positive value. Let's look at the classic example, f of x equals x squared. If we test a value like x equals 3, f of 3 is 3 squared, which is 9. Now, let's test its negative counterpart, x equals negative 3. f of negative 3 is negative 3 squared, which is also 9. As you can see, f of negative 3 equals f of 3. This holds true for all x. Let's prove it algebraically. We start with f of negative x. We replace x with negative x in the function's rule. So f of negative x equals negative x, all squared. Squaring a negative number makes it positive, so this simplifies to x squared. And x squared is just our original function, f of x. Therefore, f of x equals x squared is an even function. Graphically, even functions have a very distinct property. The graph of an even function is symmetrical about the y-axis. This means if you fold the graph along the y-axis, the two halves would perfectly overlap. For f of x equals x squared, you can see this symmetry clearly. Now, let's move on to odd functions. A function f of x is odd if, for every x in its domain, f of negative x equals negative f of x. This means plugging in a negative value gives the negative of the result you'd get from plugging in the positive value. Let's consider the function f of x equals x cubed. If we test x equals 2, f of 2 is 2 cubed, which is 8. Now, let's test x equals negative 2. f of negative 2 is negative 2 cubed, which is negative 8. Notice that f of negative 2 is the negative of f of 2. This relationship holds for all x. Let's prove it algebraically. We start with f of negative x. This is negative x, all cubed. We can write this as negative 1 cubed times x cubed. Negative 1 cubed is negative 1, so we get negative x cubed. Since x cubed is f of x, we have shown that f of negative x equals negative f of x. Therefore, f of x equals x cubed is an odd function. Graphically, odd functions also have a unique symmetry. The graph of an odd function has rotational symmetry about the origin. This means if you rotate the graph 180 degrees around the point 0, 0, it will look exactly the same. For f of x equals x cubed, you can see this rotational symmetry. It's important to remember that not all functions are even or odd. Many functions are neither. A function is neither even nor odd if it fails both tests. That is, f of negative x is not equal to f of x, and f of negative x is not equal to negative f of x. Let's look at an example. Consider the function h of x equals x squared minus 2x plus 3. To test it, we find h of negative x. We substitute negative x for x in the expression. This gives us negative x squared minus 2 times negative x plus 3. Simplifying this, negative x squared is x squared, and negative 2 times negative x is positive 2x. So h of negative x equals x squared plus 2x plus 3. Now let's compare this to our original function, h of x. Is h of negative x equal to h of x? No, because of the plus 2x term. Is h of negative x equal to negative h of x? Negative h of x would be negative x squared plus 2x minus 3, which is also not the same. Since it fails both tests, h of x is neither even nor odd. Let's work through a few more examples to solidify this concept. First, let's determine if f of x equals 1 over x is even, odd, or neither. We start by finding f of negative x. This is 1 over negative x, which is the same as negative 1 over x. Notice that negative 1 over x is the negative of our original function, f of x. So f of negative x equals negative f of x. which means f of x equals 1 over x is an odd function. Next, let's test g of x equals x to the power of 4 plus x squared. We find g of negative x. This is negative x to the power of 4 plus negative x squared. Since both powers are even, the negative signs disappear. We are left with x to the power of 4 plus x squared, which is our original function, g of x. So g of negative x equals g of x, making g of x an even function. This pattern is a useful shortcut. A polynomial with only even powers of x is always an even function, and a polynomial with only odd powers of x is always an odd function. Let's tackle a more complex problem involving even functions. Suppose we have a function f of x equals the quantity 2x plus 3 times the quantity x plus a, where a is a constant. We are told that f is an even function, and we need to find the value of a. The key here is to use the definition of an even function. F of negative x must equal f of x. First, let's find f of negative x. We substitute negative x for x in the expression. This gives us the quantity 2 times negative x plus 3 times the quantity negative x plus a. Now we set f of negative x equal to f of x. So the quantity negative 2x plus 3 times negative x plus a must equal the quantity 2x plus 3 times x plus a. To solve for a, we can expand both sides of the equation. Expanding the left side gives us 2x squared minus 2ax minus 3x plus 3a. Expanding the right side gives us 2x squared plus 2ax plus 3x plus 3a. Since this equation must be true for all values of x, the coefficients of the corresponding powers of x on both sides must be equal. Let's compare the coefficients of x. On the left, the coefficient is negative 2a minus 3. On the right, it's 2a plus 3. Setting them equal, we get negative 2a minus 3 equals 2a plus 3. Now we solve this simple linear equation for a. Subtracting 2a from both sides gives negative 4. A minus 3 equals 3. Adding 3 to both sides gives negative 4. A equals 6. Dividing by negative 4, we find that a equals negative 6 over 4, which simplifies to negative 3 over 2. So for the function to be even, the constant, a, must be negative 3 over 2. Now let's move on to our second main topic, sign diagrams. A sign diagram is a visual tool that helps us understand when a function is positive, negative, or 0 without having to draw a detailed graph. It's essentially a number line that shows the sign of a function in different intervals. To construct a sign diagram for a function f of x, we need to find two things: its zeros, which are the x values where f of x equals 0, and any values of x where the function is undefined, like vertical asymptotes. Let's look at a simple example. F of x equals the quantity x plus 2 times the quantity x minus 1. First, we find the zeros by setting the function equal to 0. This gives us x equals negative 2 and x equals 1. These are the critical points for our sign diagram. We draw a number line and mark these zeros. These points divide the number line into 3 intervals: x less than negative 2, x between negative 2 and 1, and x greater than 1. Now, we need to determine the sign of the function in each interval. We can do this by picking a test value from each interval and plugging it into the function. For the interval x greater than 1, let's pick x equals 2. f of 2 is 4 times 1, which is 4. Since 4 is positive, we put a plus sign in this interval. For the interval between negative 2 and 1, let's pick x equals 0. f of 0 is 2 times negative 1, which is negative 2. Since negative 2 is negative, we put a minus sign in this interval. For the interval x less than negative 2, let's pick x equals negative 3. f of negative 3 is negative 1 times negative 4, which is 4. Since 4 is positive, we put a plus sign in this interval. And there you have it. This sign diagram tells us that the function is positive for x less than negative 2 and x greater than 1, and negative for x between negative 2 and 1. There's a very important rule to remember when constructing sign diagrams, especially when dealing with repeated factors. The rule is this: when a function has a linear factor with an odd power, the sign changes about that 0. When a function has a linear factor with an even power, there is no sign change about that 0. Let's see this in action with two examples. First, consider f of x equals 12 minus 3x squared. We start by factoring it. We can factor out a negative 3, leaving us with negative 3 times the quantity x squared minus 4. This is a difference of squares, so it factors further into negative 3 times x plus 2 times x minus 2. The zeros are negative 2 and 2. Notice that the factors x plus 2 and x2 both have an odd power, which is 1. This means we expect the sign to change at each zero. Let's test a value greater than 2, say x equals 3. f of 3 is negative 3 times 5 times 1, which is negative 15. So the sign is negative. Since the factors have odd powers, the signs will alternate. So it's negative, then positive, then negative. Now for our second example, g of x equals negative 4 times the quantity x minus 3 squared. This function has only one zero, x equals 3. The factor x3 has an even power, 2. This means we expect the sign to not change at x equals 3. Let's test a value greater than 3, say x equals 4. G of 4 is negative 4 times 1 squared, which is negative 4. So the sign is negative. Because the power is even, the sign does not change at x equals 3. It remains negative on both sides. Let's apply this to a rational function, which is a fraction where the numerator and denominator are polynomials. We want to draw a sign diagram for f of x equals the quantity x minus 1 divided by the quantity 2x plus 1. For rational functions, we have two types of critical points, zeros and undefined points. The function is 0 when the numerator is 0, so x minus 1 equals 0, which means x equals 1. The function is undefined when the denominator is 0. So 2x plus 1 equals 0, which means x equals negative 1/2. We mark these 2 points on our number line. It's good practice to use a solid dot for a 0 and an open circle or a dashed line for an undefined point. Now, let's test the intervals. The factors x1 and 2x plus 1 both have odd powers, so we expect the sign to alternate. Let's test a value greater than 1, say x equals 2. f of 2 is 1 over 5, which is positive. So we put a plus sign in this interval. Since the signs alternate, the interval between negative 1/2 and 1 must be negative, and the interval less than negative 1/2 must be positive. Our final topic is solving inequalities. This is where sign diagrams become incredibly useful. An inequality is a statement that one expression is greater than, less than, greater than or equal to, or less than or equal to another. A common mistake is to treat inequalities like equations, especially when multiplying or dividing by a variable. Let's see why this is wrong. Consider the inequality 3 is less than 5. If we multiply both sides by a positive number, say 2, we get 6 is less than 10, which is still true. The inequality sign doesn't change. But what if we multiply by a negative number, say negative 2? We get negative 6 and negative 10. Is negative 6 less than negative 10? No, it's greater. We must reverse the inequality sign to make the statement true. This is the crucial rule. Multiplying or dividing an inequality by a negative number reverses the sign. Because we don't know if a variable is positive or negative, we cannot multiply or divide an inequality by a variable. Instead, we use a reliable algebraic method. Here are the steps. First, rearrange the inequality so that one side is 0. Second, factor the non-zero side completely. Third, draw a sign diagram for the expression. Finally, use the sign diagram to find the solution. Let's solve a quadratic inequality using this method. We want to solve the inequality 3x squared plus 5x is greater than or equal to 2. Step 1. Make the right-hand side 0. We subtract 2 from both sides to get 3x squared plus 5x minus 2 is greater than or equal to 0. Step 2. Factor the left-hand side. This quadratic factors into the quantity 3x minus 1 times the quantity x plus 2. Step 3. Draw a sign diagram for the expression 3x1, x plus 2. The zeros are x equals 1/3 and x equals negative 2. Both factors have odd powers, so the sign will alternate. Testing a value greater than 1/3, like x equals 1, gives a positive result. So the diagram is plus minus plus. Step 4. determine the solution. We are looking for where the expression is greater than or equal to 0. This corresponds to the positive intervals on our sign diagram. So the solution is x is less than or equal to -2, or x is greater than or equal to 1/3. We use or equal to because the original inequality included it. Sometimes the algebraic method can be complicated. In these cases, a graphical method can be very effective. Let's solve the inequality. The quantity 3x plus 1 divided by the quantity x minus 2 is less than or equal to 2x minus 6. The graphical method involves graphing both sides of the inequality as separate functions and finding where one graph is below the other. Let's define y1 as the left side, 3x plus 1 over x minus 2, and y2 as the right side, 2x minus 6. We then graph both functions on the same set of axes. y1 is a hyperbola with a vertical asymptote at x equals 2. y2 is a straight line. Next, we find the points where the two graphs intersect. Using a graphing calculator, we find two intersection points, one at x equals 1 and another at x equals 5.5. The inequality asks for where y1 is less than or equal to y2. Graphically, this means we are looking for the x values where the graph of the hyperbola is below or touching the graph of the line. Looking at the graph, the hyperbola is below the line in two regions. The first is between the intersection point at x equals 1 and the vertical asymptote at x equals 2. The second region is to the right of the intersection point at x equals 5.5. So, the solution is x is greater than or equal to 1 and less than 2, or x is greater than or equal to 5.5. Notice that we use a strict inequality for x less than 2 because the function y1 is undefined at x equals 2. Let's quickly recap what we've covered today. We started by defining even functions where f of negative x equals f of x, and odd functions where f of negative x equals negative f of x. We saw that even functions are symmetric about the y-axis, and odd functions have rotational symmetry about the origin. Next, we learned how to construct sign diagrams by finding zeros and undefined points, and using test values or the sign change rule to determine the sign of a function in different intervals. Finally, we applied sign diagrams to solve inequalities algebraically, and we also explored a graphical method for more complex cases. Remember the key rule. Reverse the inequality sign when multiplying or dividing by a negative number. These concepts are fundamental to understanding the behavior of functions and will be used extensively in your further studies. Now, here are some practice questions for you to try. Here are 5 practice questions. Pause the video, work through them, and then check your answers on the next slide. Question 1. Determine if the function f of x equals x cubed minus 3x is even, odd, or neither. Question 2. Draw a sign diagram for the function g of x equals the quantity x plus 1 squared times the quantity x minus 2. Question 3. Solve the inequality x squared minus 5x plus 6 is less than or equal to 0. Question 4. Solve the rational inequality. The quantity x plus 4 divided by the quantity x minus 3 is greater than 2. Question 5. Suppose h of x equals the quantity x plus b times the quantity x minus 2 is an odd function. Find the value of the constant b. Here are the answers to the practice questions. Compare your solutions to these. For question 1, f of negative x equals negative x cubed plus 3x, which is negative f of x. So it's an odd function. For question 2, the sign diagram has a 0 at x equals negative 1 with an even power, and a 0 at x equals 2 with an odd power. The diagram is minus, minus, plus. For question 3, factoring gives x2, x3 is less than or equal to 0. The sign diagram is plus, minus, plus. We want the negative interval, so the solution is x is greater than or equal to 2 and less than or equal to 3. For question 4, rearranging gives negative x plus 10 over x minus 3 is greater than 0. The zeros are x equals 10 and x equals 3. The sign diagram is minus, plus, minus. We want the positive interval, so the solution is x is greater than 3 and less than 10. For question 5, setting h of negative x equal to negative h of x and expanding gives negative x squared plus 2x minus b, x plus 2b equals negative x squared plus 2x minus b x minus 2b. Comparing constant terms, we get 2b equals negative 2b, which means 4b equals 0, so b equals 0. Thank you for watching. Keep practicing these concepts, and you'll master them in no time.